All right, good afternoon. In this video, what I'll be doing is I'll be dealing with problems and solving problems that pertain to the chapter on quantum mechanics. Okay, so quantum mechanics is dealing with little quanta of energy and identified a distinguishable one quanta of energy, one little packets of energy. So I'll be solving problems that pertain to quantum mechanics as well as how they pertain to chemistry. Okay, so the first question reads, cobalt-60 is a radioactive isotope used to treat cancer. A gamma ray emitter by this isotope has an energy of 1.33 mega electron volts. Mega means a million. Mega electron volts. 1 electron volt is equal to 1.602 times 10 to the minus 19th joules. Minus 19 joules. What is the frequency in hertz? And what is the wavelength in meters of the gamma ray? Okay? So to start, we want to convert this into joules because we're used to dealing with things in joules. So we can say that this is equal to 1.33 times 10 to the 6th electron volts, right? We can then say 1 electron volt is equal to 1.609 times 10 to the minus 19th joules. If we do this arithmetic very quickly, this becomes equal to 2.14 times 10 to the negative 13th joules. So that's going to be the energy in joules. We've converted that. Now, we need to find the frequency. Well, E is equal to h nu, all right? Nu is equal to E upon h. We just found the energy. So the energy is 2.14 times 10 to the minus 13th joules divided by Planck's constant, which is 6.626 times 10 to the negative 34 joule second. The joules cancel. We now have inverse seconds, which is the unit for hertz. We do this calculation. This becomes equal to 3.23 times 10 to the 20th inverse seconds, but 1 inverse second is equal to a hertz. Okay. Now the last one states we need to find the frequency. Well, kind of an old geeky science joke is what's nu? It's going to be c over lambda. And so if nu is equal to c over lambda, then lambda, which is the wavelength, is equal to c over frequency. So the symbol here is going to be our frequency. C is the speed of light, and so that's 3 times 10 to the 8th meters per second divided by the frequency we just found here. That's 3.23 times 10 to the 20th inverse seconds, which is what a hertz is. So the inverse seconds cancels with the inverse seconds there. We're left in units of meters, and this is going to be 9.29 times 10 to the negative 13th meters, which is where gamma radiation exists. Okay? This next question reads, one reason carbon monoxide is toxic is that it binds to the blood protein hemoglobin more strongly than oxygen does. The bond between hemoglobin and carbon monoxide absorbs radiation at 1953 wave numbers or inverse centimeters. The units of the reciprocal of the wavelength in centimeters. That's what this is. We want to calculate the wavelength in both nanometers and angstroms and the frequency in hertz of the absorbed radiation. Now, if this is going to be the wave number, we can find the wavelength by taking the inverse of that. So the wavelength is going to be equal to 1 over 1953 centimeters, which is equal to 5.14 times 10, 5.12, I had to look at my notes, 2 times 10 to the minus 4th centimeters is going to be the wavelength. Now, if we want to convert that into nanometers, we start with 5.12 times 10 to the negative 4th centimeters, which is what we found there, that's our wavelength, we know that for every 1 centimeter, there are 10 millimeters. All right. For every 1 millimeter, there is 1,000 micrometers. Okay. Now, for every 1 micrometer, there is 1,000 nanometers. So we can go through and do that calculation, and this comes out to 512 nanometers. Now the next one, it wants it in angstroms. So we could start with the 512 nanometers, and for every 1 nanometer, there is 10 angstroms. The unit of angstroms is a unit that's used a lot when you're determining bond length. And so it's kind of on the order of the length of a bond. So this becomes 5,120 angstroms. And the symbol of an angstrom is an A with basically a halo over it. Next, it wants us to determine the frequency. And so we know frequency is equal to C over lambda. This is the Greek symbol nu. If you ask me, hey, what's nu? I'm going to tell you, hey, it's C over lambda. Now, C is typically written as 3 times 10 to the 8th meters per second, or we can write C as 3 times 10 to the 10th centimeters per second. We can then now divide that by our wavelength in centimeters. So the only reason I converted the speed of light into centimeters is because the wavelength that we calculated was in centimeters. Oops, put the centimeter there. The centimeter cancels with that. And what we get for a frequency now is going to be equal to, that becomes 5.86 times 10 to the 13th hertz, or remember, hertz is equal to an inverse second. All right. Next question that we have states, use the Rydberg equation to find the wavelength in nanometers of a photon emitted when a hydrogen atom undergoes a transition from n equals 1, so that'd be the first state, to n equals 3, which would be the third state. All right. First thing I'm going to do is I'm going to write down the Rydberg equation. So the Rydberg equation is, I'm going to write a little bit more than that. E equals h nu, which is, this is going to be the energy. H is Planck's constant. Nu is the frequency. We can say that that's equal to hc over lambda, because nu is c over lambda. And this is going to be equal to, this is Rydberg's constant, 2.18 times 10 to the negative 18th joules times 1 over n F squared minus 1 over n I squared, that quantity. All right. Now what we know is, we know that the transition is from 1 to 3. Okay, so let's write this out. And what we're ultimately looking for is, we're looking for the wavelength. So we don't need necessarily worry so much about the energy. We're just going to write this as hc upon lambda is equal to a negative 2.18 times 10 to the negative 18th joules times 1 over. Now the final state is the third state, so that becomes 3 squared minus 1 over 1 squared. All right. We do this arithmetic and we find out that hc upon lambda is equal to, you do this math, this becomes, this is 1 over 9 minus 1, which is going to give us a negative number. So this would be a negative number, that will be a negative number, so we end up being a positive. So this now is 1.94 times 10 to the negative 18th joules. All right. We're looking for lambda, and so lambda is going to be equal to now hc upon 1.94 times 10 to the negative 18th joules. All right. Where h is 6.626 times 10 to the negative 34 joules second times speed of light, which is 3 times 10 to the 8th meters per second, divided by now our 1.94 times 10 to the negative 18th joules. The seconds cancel, joules cancel. And what we're left with now is units of meters. We do the arithmetic, and our lambda is equal to 1.03 times 10 to the negative 7th meters. Okay? All right, this next question states, how fast must a 142-gram baseball travel to have a de Broglie wavelength equal to that of an X-ray photon whose lambda is 100 picometers? All right. Now, the de Broglie wavelength is looking at matter as though it were a wave. All right. And the equation for the de Broglie wavelength is lambda is equal to h upon p, where p is the momentum, and that's equal to mass times velocity. So therefore, the de Broglie wavelength is h upon m times v. And what we're looking for is we are looking for the velocity. And so our velocity, if we solve this for velocity, is going to be velocity is h upon m lambda. All right? Now the lambda that's given to us is 100 picometers. All right? 100 picometers. Now, if you remember, you have meters, so we can say 1 meter. And so we have meters, and then we do millimeters, and then we do micrometers, so that's -6. We do nanometers, which is -11 or -9, and then after that we have picometers, so that's -12. So it's 1 times 10 to the 12th picometers is equal to 1 meter. So the picometers cancel, and what we end up with is we have 1 times 10 to the negative 10th of a meter. Okay, so now we can plug that into our equation for our velocity, and our velocity, the h, is 6.626 times 10 to the negative 34th joule second, divided by the mass, which is 0.142 kilograms, times the wavelength we just got done finding, which is 1 times 10 to the minus 10th meters. All right. We go through and do this calculation, we're going to end up with what is called, what's going to be meters per second, and this equation is 4.67 times 10 to the negative 23rd meters per second. We're dealing with quantum numbers, and what the question states is give all possible m sub l. So m sub l is going to be the magnetic quantum number. It's going to have values of -L to +L. The magnetic quantum number, this has to do with the orientation of the orbital within space. We're going to find the m sub l's for this. All right. From, say, L, which is going to be the angular momentum quantum number. This is going to determine whether it's S, P, D, or F. And N is going to be the principal quantum number, basically the orbital in which the electron resides in. So for A, if we have L is equal to 3, then m sub l is going to be equal to a -3, -2, -1, 0, 1, 2, and 3 is going to be the possible values if we happen to have L is equal to 3. Now if N is equal to 2, if N is going to be equal to 2, then the values we can have an L, then is going to be equal to 1 because L is equal to N minus 1. So if we happen to have an L which is equal to 1, then the m sub l can be equal to -1, 0, and 1. We can also have an L for this which is going to be equal to 0, and then m sub l is going to be equal to 0 as well too. Now for this case we have an N, so the principal quantum number is 6, and L is equal to 1, Therefore, m sub L is equal to a minus 1, 0, and 1. Okay? If you have any questions, please let me know. This problem, once again, has to deal with quantum numbers. And the question states, are the following combinations allowed? If not, show 2 ways to correct them. So for the first one, we have n equals 1, L equals 0, m sub L is equal to 0. Now, the value of L has to be at least 1 minus n. 1 minus n is going to give us L. So this is a good combination. M sub L is equal to plus or minus L. And so since L is 0, m sub L can be 0 as well. So this is allowed. That's a good one. For B, we have n equals 2, L equals 2, n sub L is equal to plus 1. As I just got done stating, L has to be equal to n minus 1. So the problem lies here. This is not allowed. So what is going to be the correction for this? Well, there's 2 corrections. N either has to increase by 1, so n has to be equal to 3, because in that case, then L would be 1 less than 3, or L has to be equal to 1 if we're going to keep n the same. So those are the 2 corrections there. Letter C, we have n is equal to 7, L is equal to 1, and m sub L is equal to a plus 2. So let's just first start with n. N is equal to 7. L has to be at least 1 less than 7, and so that's fine. L can be any value from 6 down to 0, because that would then be n. It would be L is 1 less than n. So L can be any value of 6, 5, 4, 3, 2, 1, 0. M sub L is equal to plus or minus L. Nothing greater, nothing less. And so here we have a problem. So this is not allowed. And it's because of these 2. Now the fix for this is going to be either L is equal to 2, which is allowed because it's still less than 7, or our m sub L must be equal to 1, plus 1 if we're going to stay positive. Okay? For the last one, what we have is we have n is equal to 3, L is equal to 1, m sub L is equal to a minus 2. Now, as we just got done stating, we said that L has to be at least 1 less than n. So L in this case, since n is 3, L can be either 2, 1, or 0. All right. M sub L, once again, has to be, if L is going to be 1, then m sub L has to be either 1, 0, or minus 1. Because of that, this is not allowed. It's not allowed. So the way we can correct this is that L is equal to 2, which will still be fine so long as n is equal to 3. If L is 2, then m sub L can certainly be minus 2. Another fix for this is that if we're going to keep L as 1, then m sub L would be equal to a negative 1. All right? If you have any questions on any problems in this chapter, feel free to let me know. Okay?